At this point, you've completed the Desmos activity. This is where we left off from the last video. These were different transformations of y equals sine x, and we had talked about the fact that the number in front of the sine seems to change how high the graph goes, right? The y equals 3 sine x, that's the blue one, goes all the way up to the top, whereas the negative 3 sine x goes all the way down to the bottom, and that 1/3 only goes 1/3 of the way up instead of going all the way up to the top. So that seems to change the amplitude, right? The number in front of the sine changes the amplitude. How about the second round of them? The second round was the sine of 2x and the sine of x over 2. So here I can actually change these colors, right? Because you notice I got 2 reds, but I don't want 2 reds. So how about a red and a green? There we go. All right. So the original one is the red function. The black one is the sine of 2x, and the green one is the sine of x over 2. That looks like it changes the period. And you notice that the black function has a sine of 2x, and it moves much faster. So it actually completes 2 cycles between 0 and 2 pi rather than just 1. The green one, on the other hand, completes just half a cycle from 0 to 2 pi, and the other half of the cycle from negative 2 pi to 0. So that one has a period of 4 pi. So changing the number on the inside changes the period. Changing the number on the outside changes the amplitude. Now let's see what happens to the third round. I've got a blue one and a green one. The blue one was the sine of x plus pi over 2. So you notice what happens to this one is it moves it. Instead of it going through the axis as 0, it crosses the axis here at pi over 2. What happens to the green function? The green function is just the red function moved up 2. So putting the 2 on the outside changes the shift vertically. Putting the number on the inside shifts it horizontally. So not drastically different from when you had those like y equals parentheses x minus 2 and then square on the outside for those parabolas. It does the same thing here, right? It moves it in quote-unquote reverse of what you think. All right, so a couple of terms here. Coming to terms with trig. So amplitude is how much above and below the axis line. Sometimes we call it the midline. But that midline can shift, because go back to that green function that we just had up there a minute ago. For this one, the midline was not at the x-axis. The midline was actually at y equals 2. Right? So if I graph y equals 2, that's going to be sort of the halfway mark of that function, not the x-axis. So what I'm calling the midline could change from graph to graph. Period is one complete cycle of the graph. The graphs are periodic. And then phase shift is how much it moves left and right. So these types of equations can all be combined, right? I gave them to you in pieces. But they can be combined together to look like this. So what changes what? The a over here changes the amplitude. So the a changes the amplitude. It also can cause a reflection. You notice the one that we graphed that had a negative 3 reflected it across the x-axis. So it can do one, the other, or both. That b value is going to change the period. That h value is going to cause a phase shift. All right, so a phase shift is left and right. And then that k is going to be a vertical shift. So, of course, it could go down also, right? It doesn't only have to go up. Vertical shift could go up or down. But that's how it works. We call y equals sine x the parent function. If you wanted to transform cosine, then you would have exactly the same thing with cosine x, except you would be changing the amplitude, the period, the phase, and the vertical shift of cosine x. So here's a nice little picture. Obviously, I did not draw this. I got this out of the book. But what does that number in front of the x tell you? Well, it tells you the period. There's 2 ways to think of it. If I'm given a graph and I want to find the period, sometimes I just look and go, well, all right, how many cycles are there? Usually this graph goes from 0 to 2 pi, but if it creates 2 cycles between 0 and 2 pi, now I'm going to put a 2 in front of there. Same thing with the other graph that was a half. If it only creates half a cycle, I put a 1/2. The other thing you can do is you can set up an equation where the period is 2 pi over b. So b is the number before the x. So the period is 2 pi divided by that. if the original graph has a period of 2 pi. If it's something like tangent that has a period of pi, then you would just use pi over b. Amplitude is not a positive or negative number, so you notice here it says the amplitude is the absolute value of a. Now, I'm talking about phase and phase shifts and moving things left and right. Two waves are in phase if the waves coincide. So there's all kinds of applications for whether things are in phase or not. Alternating current can be in phase or not in phase. Current flow. I do a lot of work with sound engineering. If you set up something left and right channel and the sound waves are not in phase, then two things can happen. One is that the audio just sounds really weird. But the other thing is it can cancel out the vocals, because sometimes, especially some of the older recordings, are recorded very differently in the left channel than they are in the right channel. And it's expected that when you play them back, those sound waves on the left channel and the right channel are following along with each other. If they get out of phase from each other, then sometimes the vocals just disappear and all you hear is the music in the background. You're going, there were words to this song last time I heard. Oh, and sometimes it can be as simple as switching two inputs to a mixer or something like that can knock a system out of phase. So it is important that things are in phase sometimes, and it goes beyond just, making them in phase for the pre-calc test. Out in the real world, there are applications to these things. So what do these functions look like? I gave you two functions over here. If you want to graph them on Desmos, you could do that and see what they look like. It turns out you're going to get the same function. Right? If you put a value in for x, you're going to get the same value out for y in both of them. It is easier for me to work with the function on the top than the one on the bottom. Why? Well, here, let's go to try to graph it. What's going to happen to this thing? Well, I'm going to start off with my cosine function. And then this says I'm going to shift it to the right pi over 4. Right? That's my phase shift. Then I'm going to realize that the period changes. So this tells me I can fit two cosine graphs from 0 to 2 pi. So instead of two cosine graphs from 0 to 2 pi, another way of saying it is I can fit one cosine graph from 0 to pi. And then the other things that are going to happen is the amplitude is going to change, right? So the amplitude is now going to be 3. It's going to reflect across the x-axis. That's what the negative sign tells me. And then it's going to go up 5. Now, what order do these things happen in? Well, what if I started with plain old cosine x? Right? Cosine x starts at 0, 1. It goes down and back up again. Well, what happens if I reflect that across the x-axis? Now, instead of starting at 0, 1, it's going to start at 0, negative 1. It's going to go up and back down again like that. So that takes care of the cosine, takes care of the reflection across the x-axis. Now, it needs to do two things in sort of a specific order. It needs to move to the right pi over 4, and then it needs its period to change from 2 pi to pi. The other thing that's going to change is the amplitude, and actually I can change that now. Instead of going from negative 1 to 1, look at that. By math magic, it now goes from negative 3 to 3. So normally this would be at negative 3 on the y-axis, 0 on the x. But now, let's make it go negative 3 pi over 4. All right, so I'm shifting it to the right pi over 4. Well, if I do that, then instead of ending at pi, it's going to end at pi plus pi over 4, which is over here. What's going to happen in between? Well, the halfway mark of that is going to be the maximum, so it happens between pi over 2 and pi. Right, so halfway in between there, looks like around here, it hits its maximum. So this graph is going to come up. It's going to cross at pi over 2. A maximum here, turn around, try to make it smooth. It's going to cross at pi, then down here. And then, what's it going to do from there? It's going to continue, right? It's going to continue on this other side. And if it crossed here at pi over 4, I'll bet you at negative pi over 4 it's going to do the same thing. So it's got to go all the way up and back down again by the time it gets there. Nope, it's going to be up on top. That's negative pi over 4. That's the other one where it's down. All right, so whatever I do on the right side, I got to do on the left side. So look, it's going to go through the origin all the way up and back down. So now this is everything except for that plus 5 at the end. So I've got a beautiful looking graph and I've got a terrible looking axis in terms of actually making this work for the numbers I gave you. So here, can I just do this? Can I add 5 to everything and say that's 8, 7, 6, 5, 4, 3, 2. Look at that, now my graph fits. One of the points is that this thing does not cross the axis, right? That's 2, that's 1. The x-axis is way down the bottom over here. So when I push this graph up 5, it does not cross the axis. So here. All right, so here's what my graph looks like. I got to zoom out so I can see them both. You notice that the original cosine graph is the red one. It has a period of 2 pi. Every 2 pi, this thing goes bottom, top, bottom, top. This blue one does not. It starts down the bottom here, right? Pi over 4, 2. Goes up to the top here at 3 pi over 4, 8. Back down here. So it crosses at pi over 4, hits the bottom at 5 pi over 4. So instead of getting back to its starting point every 2 pi, it gets back every pi. Let's try another one. I've got the sine of 2x plus pi over 3. Now, I'd like to rewrite this first so it's easier for me to work with. So can I factor a 2 out of this x plus pi over 3? So if I pull out a 2, I'm left with an x plus. So if I divide half of pi over 3 is pi over 6. So I'm going to think of this as y equals the sine of 2 times x plus pi over 6. So what happens? I start with my good old sine function, right? Remember the sine of 0 is 0, so this is the one that goes up, down, back up again. That 2 in front is going to change it so I can fit 2 sine curves from 0 to 2 pi. So instead of it going from 0 to 2 pi, it's actually going to go from 0 to pi. And that's pi over 2, and so forth. Before I do that, I'm going to shift it to the left pi over 6, right? So that plus pi over 6 means I'm going to shift it to the left pi over 6. So what are these markings on my graph? That's a pi over 6. That's a 2 pi over 6. So instead of it starting at 0, going up and back down again, now it's going to start at negative pi over 6. And what else? It's not going to take 2 pi before it goes all the way across. It's only going to take pi before it goes all the way across. So if that's negative pi over 6, that's 5 pi over 6. That's one complete cycle. What's halfway in between there? And if you're not sure, count the blocks. 1, 2, 3, 4, 5, 6. So 3 blocks is the halfway mark. So this graph is going to go up. It's going to hit a maximum over here and come down. Then halfway in between, it's going to hit a minimum and come back up. So that's one complete cycle. Can I do it again? Let's do it again. Halfway in between, half of half, half of half. Up, down, down, up. And then it just continues forever that way and forever that way. All right, so pulling the 2 on the outside made it easier because now I realize that the period is 2 or the b value is 2. And so I can fit 2 graphs inside of that 2 pi range. So half of 2 pi is pi. Every pi this thing repeats. Now, all right, so this graph asks us to write 2 equations, one in terms of sine, one in terms of cosine for the graph that's given. Now, the cosine one is easy because this kind of looks like y equals cosine, right? It starts on the top, it goes down and back up again. So it looks like y equals cosine of x, except you notice that instead of it going from 0 to 2 pi, it goes from 0 to pi. So if I continued this graph down and back up again, by the time I got to 2 pi, I'd have 2 cosine graphs in there. Okay, that was the easy one. What's the hard one? Well, the hard one is, could this be sine of x? It could be sine of x, but where would it have gone? It would have gone this way to negative pi over 4. How do I know? Look where the corresponding point is on the other side. That's positive pi over 4. So on the other side, I get negative pi over 4. So I get y equals the sine. Just like for the cosine of 2x, we got to do the 2 for the sine of x. And remember, it's the opposite, so it's plus pi over 4. So it shifts pi over 4 to the left, and then the period is shorter, so I can fit 2 complete cycles from 0 to 2 pi rather than just 1. So notice that I can write two different equations for the same graph, one with sine and one with cosine. I'm using the fact that cosine is just sine shifted over a little bit. All right, last couple examples. Let's make another video because this is getting long.